This is example 12.3 from Discovering Design with Chemistry. In this one we have three different things that all ask, is the following reaction a redox reaction? If so, what is reduced and what is oxidized? And then what is the oxidizing agent and what is the reducing agent? And I'm going to move our rules along to the side as we do these, so you'll have to pardon with me a little between each example. So the first one gives us this equation right here. And so we're going to start by just lining up our different oxidation states underneath. Let me go ahead and move this to the side a little bit. So zinc is just a singular element, and so that's going to be 0. Copper has a 2+ charge, and so that's an ion composed of only one atom. So for rule number 1, it's equal to the charge of the ion, so that's 2+. Zinc on this side has the same thing happening. It's an ion that gives a charge of 2+, therefore its oxidation state is equal to that charge. And the last one is copper. We're back to just the element copper, single element, and so its oxidation state is 0. So let's look at what happened here with these. So zinc went from a 0 to a 2+. So zinc went from 0 to 2+. You don't have to write this part, I'm just writing it to help us see what's happening. And then copper went from 2+ to 0. So you can see that copper's number went down, so that you can think down as reduced. So copper was reduced, and the zinc must have been oxidized since it's the other one, and its number went up. But reduced I feel like is easier to remember because the number goes down, therefore it's being reduced. So zinc is oxidized, copper is reduced, and because the zinc was oxidized, that means zinc was the reducing agent because it made the copper become reduced by moving those charges around. And then copper, because it was reduced, is the oxidizing agent. I have no idea why I put an S on the last one, because the copper was reduced, therefore it was the oxidizing agent. Okay, so let's look at the next example. Let's move our rules over here so we can keep track of them. All right, so our next one has carbon dioxide and hydrogen gas combining to form carbon monoxide and water in the form of water vapor. All right, so in the first one, we don't have anything that tells us about carbon, and the only one that tells us about oxygen is rule number 6. You can look through the other ones first. It's not composed of one atom. It's not and just an element. We will use the fact that this is going to have equal to the total charge, which is 0 for the total charge. It's not fluorine or hydrogen, so we're going to go with rule number 6 and know that oxygen has an oxidation state of -2, but there are 2 of them, which means to balance that out and keep carbon dioxide at 0, the copper must have an oxidation state of +4. I'm going to keep this one down here in parentheses so I can remember how I got the +4, but the 2- is the important one that we care about. So hydrogen is just a homonuclear molecule, and so that is 0. And then we have another one here. Just like with the carbon dioxide, carbon monoxide is the same elements being put together in a molecule, but we don't have any different rules, and so we're still going to have to go with rule 6 and give oxygen the 2- charge, which means, because there's only one of them this time, to keep this overall charge of 0 that this molecule has, carbon this time has a 2+ charge. And then down to this last one, we do have a rule about hydrogen, and that's in the always true section. So let's start there. Hydrogen has an oxidation state of 1+, and there are 2 of them. So I'm going to write that so we can figure out oxygen. Water does not have a charge, and so we have 2 pluses. So to balance that out, we need 2 minuses. All right, so let's compare. So copper went from 4+ on the left to 2+ on the right, and then hydrogen went from 0 on the left to 1+ on the right. Let's pick a different color. And then oxygen, I'm going to put a little swirl on the O because it helps me tell it apart from a 0. It was, remember, we're only looking at this one, it was a 2- on the left, and both places it's a 2- on the right. So oxygen didn't change, so we can just ignore that one. but we can see with the others what happened. So which one went down in number? Carbon. So this one was reduced. So carbon was reduced. Oh, that's spelled wrong. I'm about to spell somebody's name there. Carbon. And then hydrogen's the other one. So hydrogen was oxidized. All right, so before we decide the oxidizing agent and the reducing agent, you need to know that it's referring to the reactants, not just the atoms whose oxidation states changed. And so hydrogen was oxidized, but hydrogen by itself wasn't the reducing agent. It's this whole thing. So hydrogen gas is the reducing agent. And then same thing for the other one. Carbon was reduced, but carbon by itself isn't the oxidizing agent. It's where the carbon came from. So CO2 is our oxidizing agent. Don't worry about not being able to read my handwriting, as long as you understand what that's supposed to say. So carbon dioxide is the oxidizing agent as a whole molecule. All right, so let's look at the last example. And let's move our rules over here so that we can follow them. All right, so let's start by figuring out the charge of everything involved in this. My rules are kind of going off the side there a little bit. There we go. Oh, no, that's still, there we go. All right, so let's look at the first one. We have FeCl3. For that one, we're not going to be able to use the ion number 1 through number 5. It doesn't have any, but we can use number 7 to figure out that chlorine is probably going to have a -1, and there are 3 of them. So I'm going to put in parentheses 2 more, so you can see there are 3 minuses there. And that means, as this has an overall charge of 0, Fe must be 3 plus to balance that out. This right here is a polyatomic ion, and so we have the overall charge is 0, but this part is 1 plus and this part is 1 minus. So we're going to put 1 plus under this one, and then we have to kind of separate out our O and our H a little bit. I'm not going to be able to fit it very nicely, so I'm going to kind of drag down little pointers to show that I have more room. All right, so we're going to use rule number 5 because it's the first one that applies to this one, and say hydrogen is 1 plus. Now we want this to have an overall charge, this section right here, to be 1 minus. We don't want it to be 0. If it were 0, we would just put 1 minus here. But that's not the case. We want it to have a -1 charge. So if we only have 1 positive, we need 2 negatives. 1 to bring it down to 0 and 1 more to bring it down to -1. So 2 minus, which actually lines up with rule number 6 anyways. All right, next we have this one. Again, here's our OH, our polyatomic ion in there. And so you can kind of see that we've got a 3 here, an imaginary 1 here, and you can move those up like you would when you're doing other atomic compounds. So Fe is going to have a 3 plus charge. And then OH as a set is going to have a 1 minus charge. But again, we have to take the different pieces, because oxygen's rule is in the usually true and hydrogen's rule is in the always true. We're going to go with number 5, the always true of this is +1. And because we want the overall charge to be -1, that means we need 2 minuses to balance out that 1 positive. So 2 minus. And then our last one, this is just a regular old salt. So we know this one, this is going to be 1 plus and 1 minus, because that's just, that's our ionic compound that we can use to figure it out. Okay, so looking at these, let's compare each of our things. So we have iron, it was 3 plus on one side, is 3 plus on the other. Chlorine is 1 minus over here, 1 minus over there. And I'm going straight across, starting with the reactants to find these. Next, we're going to do sodium, which is +1 on this side and +1 on that side. Then we have oxygen, which is 2 minus, oh, I wrote it backwards. 2 minus on this side and 2 minus on the other side. And then last we have hydrogen, which is 1 plus on this side and 1 plus on the other side. So if you look at this set of numbers, you can see that going from the reactant side to the product side, nothing changed its oxidation state. And so this is not a redox reaction. So no, that means we don't have to answer that one or that one. All right.